Hello everyone. I'm Gitanjali Jaina. I'm a PhD scholar from IIT Delhi, and I'm also a PMR FTA for this course, Introduction to Laser, which is taught by Professor M.R. Sinha from IIT Delhi. So, in each lab section, we will cover the concept, we will cover the weekly concept that has been taught in the course, and as I will and we will I will clarify the doubts, the assignment doubts that you must be having for the weekly assignment. And besides, I will also solve few problems that will help you to understand the concept as well as for practice purpose also. So without further delay, let us start the section. So in week 10 is all about pulse laser. So we'll go through different types of pulse laser and how we will achieve that and what is the condition that is required to get a pulse laser and how we can detect a pulse laser in experiment. So pulse laser, let us see what is the definition. So as the name indicate, the pulse laser consists of pulses which are periodic in nature. So if you look at this figure, so it's the power output versus time for a continuous wave laser. So for a continuous wavelength laser, what we have the output that we detect. It is constant and it is uniform over all the time. But if you look at the second figure, so Ananya is you have joined now. So I was just starting the session about the pulse laser and all. So before that, as you have joined, let me ask whether you have any doubt in the week 9 assignment, in any of the problem of week 9 assignment. You can write down your theory in the chat box or you can unmute yourself and ask your doubt. In the meantime, let me go through the concept. Okay. So as I said, for a continuous wave laser, we have power output which is uniform over all the time. But for the pulse laser, if you see this figure, consist of pulses which are periodic in nature. So these consist of pulses which are periodic in time. So if you look at this figure, so these are some schematic of a pulse laser. And T, the capital T, is the time period between the pulse, the periodic pulse, and tau, it's the full width at half of the maximum. So now we have different type of pulses. Like the pulses can be a square pulse or it can be a rectangular pulse. So there are different type of pulses that we generally see in our day-to-day life or during the experiment. So if you look at this figure, it's a rectangular pulse where the peak power is denoted by P peak, and tau is the full width at half of the maximum, and capital T is the time period between the periodic pulse. So if you are, let's say, if you are given the time period T and full width at half maximum, it is tau. Then you can calculate three important parameters of a pulsed laser. So normally we specify pulse laser using this parameter. One is the peak power, which is given by P peak equal to P average power into T by tau. And average power, it is given by P peak into tau by T. And the energy per pulse, it is given by P peak into tau or P average into capital T. So, and the pulse repetition rate, it is given by, so if you want to find out what is the pulse repetition rate, which is PRR, is given by 1 by T. So how frequently the pulses is repeating over one interval of time. So this is PRR. So if you are given any of these, like P average given, then you can calculate P peak. From P peak, you can easily calculate what is the energy of the pulse. So don't confuse between P peak and P average. So P peak is the maximum power that the pulse have, and P average, it is the average power over one interval of time. So over one period, what is the power? So over this interval, that is T time period, what is the power contained in this region? And P peak is the highest power of the peak pulse. So this is one of the examples that the professor has discussed. One is the Q switch and DX laser. So in this case, if you have P average, it's given it is 10 watt, and pulse width, which it is given 100 nanosecond, and the repetition rate, which is the pulse repetition rate, it is 1 kilohertz. So from pulse repetition rate, you can calculate what is the time period T, which is given by 1 by P pulse repetition rate, that is 1 by 1 kilohertz. So it is 10 to the minus 3 second. And as P average is already given, then you can calculate what is the peak power of this pulse. What is the maximum power that the pulse has. So it is given by P average into T by tau. So P average is 10 watt, and capital T, it is 10 to the minus 3 second, and small tau, it is given 100 nanosecond, that is 10 to the minus 7 second. So here you can see the peak power, it is of 100 kilowatt. So although the P average is small, but peak power is 100 kilowatt. And from this, you can easily calculate what is the energy of this pulse, which is P peak into tau. So P peak we have already calculated, it is 100 kilowatt, and P tau, it is given 100 nanosecond. So that means the energy of the pulse, it is 10 millijoule per pulse. So when the pulse incident on a material, so it will deliver 10 millijoule per pulse. Okay. And another parameter that is also used is fluence. So fluence is nothing but pulse energy per unit area. So if you are given a area of the sample where the laser is incidenting, then you can first calculate what is the pulse energy, and you can divide it to the area of the beam spot. From that, you can calculate what is the fluence of the sample. And the next parameter is length of the pulse. So length of the pulse, it is given by tau into C. What is the pulse width in terms of time cross C. So if you put 100 nanosecond, then and C is nothing but the speed of light, so it will come around 30 millimeter. So in this way, you can calculate what is the different parameters of a pulse laser. What is the peak power, what is the average power, and what is the energy per pulse. So next thing is what is the importance of this pulse laser? Why we are discussing this pulse laser? So the most important application of pulse laser is in optical communication. So if you recall in optical communication, which we do through fiber, so the pulses are they are sent through in terms of binary digit. So either the pulse is the digit is one, binary digit is one or zero. So in terms of one and zero, we send information through the optical fiber. So this binary digital communication, this you can make a similarity to the pulse laser. So for short interval time, the pulse laser is on, and for the next interval, it is zero. Then again, you see a pulse. then it is 0, then pulse, then is 0. So the pulse is there means it is 1, and the pulse is not there means it is 0. So using this pulse laser, we can uh, use this pulse laser for optical communication purpose. And the next is the laser ranging on detection. So for detection purposes, you can use this pulse laser where we can resolve the spatial resolution using this pulse laser. And the spatial resolution, it is limited by the length of the pulse. And we can also use it during laser surgery or precision cutting. So where we will incident the laser light to a material, and due to the high energy of this laser, what will happen? Some part where you are incidenting the, let's say you are incidenting the laser spot here, then up to this reason the material will be removed from the surface. So depending on the pattern, uh, you can make a material, or you can use it to design a nanostructure also. So we use laser for precision cutting, okay, and non-linear optical processes where the efficiency it is directly proportional to the optical power. And you can also use this pulse laser for ultra fast processes where if you want to study the dynamics of a system where the time is very small. So in that case, you can use ultra fast laser such as femtosecond laser to study the dynamics of the sample. So these are the different application of this pulse laser. So next we'll quickly move to towards what is the method of achieving the pulse laser. So how we can achieve a pulse laser uh, when you are given in materials, or if you are given a continuous wave laser, then how you can make the pulse laser. So these are the four different ways where you can generate a pulse laser. So the first one is the external modulation. Second one is the gain switching, then loss switching and mode locking. So we'll briefly go through each of these method of generating a pulse laser. So the first one is the external modulation. So we use this external modulation when we, let's say you have a continuous wave laser and we don't have a pulse laser in the laboratory. So in that case, what you can do, you can use the external modulator such as electro-optic modulator or acousto-optic modulator or electro-absorption modulator to convert the continuous wave laser to a pulse laser. So you have this continuous wave laser where P out is uniform over the time. Then using a modulator, a external modulator, you can achieve a pulsed output. Okay. And the strength of this pulse laser, the spacing between these pulses, it depends on the external modulator strength. So the example of external modulator, it is, as I've said, it is one is electro-optic modulator, and next one is acousto-optic modulator, and the next one is electro-absorption modulator. So and this what will happen if you use a modulator? So let's say you have a modulator here and you are changing the strength of this signal, which changes the modulation ability of this external modulator. Okay. So what will happen depending on the strength of this external modulator? Some part of this continuous wave laser will pass through the external modulator and some part will not be passed through the external modulator. So in this way, you can see there is a pulsed output here using the external modulator. And this external modulation, it is very useful when you have a continuous wave laser and you don't have a pulse laser. And it is essential when you want to get a pulse laser where the pulse repetition rate is high. So let's say 10 gigabits per second. So for that case, you can use the external modulator to achieve a pulse of 10 gigabits per second. And one of the drawback of this external modulator is that the energy that is stored in the external modulator, it is wasted during the off time. 1 minute. Guidance regarding the exam. Let's schedule. Should I prepare for it? Pause the semester. So regarding the exam time, that I don't have any idea, but I will talk with the NPTEL TAs because they know the details of the exam and the time. So and the about so let me tell you the exam time in the next live session. But uh, about the preparation, so I think it's easy if you follow the lecture slides and follow the lectures, and if you solve the assignment, the weekly assignment, and some additional problems that I also solved during the live session. So if you solve that, then it's really easy uh, to pass the exam. So the questions, these are more, so as I've said in one of the live session, the questions are relatively, there may be easy question, direct question, or there can be numerical question type. And some of the question will be conceptual type. So and some part of this assignment, this year, so exam, it is assignment based also. That is the similar to the question asked in your weekly assignment. The questions will be the final question will be somewhat similar, but it's not exactly similar. But there will be some modification, like the some terms, some different value. So if you so I would suggest to go through the lecture slides and the lecture videos and the weekly assignment as well as the problems that I solved during the live session. So if you go through that all, then you will easy to pass the exam. Okay. So let us move to our concept. So first one is as we are discussing, it is external modulation. And the next one, 1 minute. So next one is the gain switching. So in gain switching, what we have, so instead of applying a external modulator, what we'll do in the gain switching, will control the pump. So if you see this figure, this is the schematic of a laser oscillator. So it's a cavity with a feedback system with a pump. So now if you modulate this pump, that is if you switch on the pump and switch off the pumps, and then according to that, you can get a you can get a pulse laser output through this cavity. So if you look at this figure, so there is a loss line here, right? So this is the loss line. And to get amplification, the gain should be greater than this loss line. So let us say for the first time, for the first t equal to t0, the pump is off. So that means the loss is greater than the gain in the system. So whatever gain is achieved, it is lost uh, during the oscillation process. So because of this, what we'll see, you will see no laser output in this interval. So if you see this red line, it is laser output is zero. Now, when the pump is on, then what will happen? Gradually, the system will achieve a steady state, and whenever the pump, that is the gain in the system, is greater than the loss line, the laser will be amplified. The output will be amplified. So, in that case, what we will see, because of pump switching on this pump, we will see increase in the laser output. And again, what we'll do, we'll switch off this pump. So for this interval, you can see the pump is off. So because of switching off this pump, what will happen? Gradually, the gain will gradually decrease, and it will now coincide with this loss line. So because of that, then again the gain will decrease below the loss line. So because of this switching of this pump, what we'll see, the laser output will gradually decrease over this off time, and this process will repeat periodically when you switch on and switch off the pump period. In this way, you can generate a pulse output through this laser cavity. Okay, and one of the example of this again switching is Aurobi laser, where you switch off and switch on the flash lamp to get a pulse output. And other example is the semiconductor laser, where if you see this figure, it is a laser diode, and you change the injection current. You change the injection current to this laser output. So as you change the injection current, what will happen? You will see a pulsed output through this semiconductor laser. So let us move to our next problem then, next method. So next method is loss switching. So loss switching is of two types. So if you see, one is cavity dumping and another one is the Q switching. So in cavity dumping, what we usually do, we dump the energy stored in the cavity. So as the name indicate, the cavity dumping, the energy stored in the cavity is suddenly dumped by changing the output mirror transmittance. So if you see this figure, the figure here, so we have two mirrors, mirror M1 and mirror M2. The reflectance of the first mirror is 100%, and the reflectance of the second mirror, it can be varied from 0 to 100%. And depending on the reflectance of this two mirror, what will do, the energy stored in the cavity will be changed. So in let's say the reflectance is high, that means the energy stored in the cavity is high. But when the reflectance is low, that means the energy stored in the cavity is low. So in this way, by changing the reflectance of the mirror, you can change the pulse output. You can get a pulsed output through this laser cavity. So we'll see the schematic in our next slide. So for now, let us see what is Q switching. So Q switching in this method, what we'll do, the energy stored in the active medium. So there is the active medium inside this laser cavity. So we vary the energy stored in the active medium. So by varying the energy stored in the active medium, we'll see a pulsed output through the laser system. And what we usually do during the off time of this Q switching, the resonator Q is very high. That is, the energy stored in the cavity is very high. So now let us see what is cavity dumping. So as shown in this figure, these are the two feedback system, mirror M1 and mirror M2, and there is the active medium and a pump. And the laser, it oscillates back and forth between this mirror M1 and M2. So now So now if you see this figure, now we are changing the transmittance of this mirror. That is, we are changing the reflectivity of mirror. So what is the relation between reflectivity and transmittance? Reflectance and transmittance. So transmittance, it is given by 1 minus R. So we are changing the transmittance means we are changing the reflectance. Okay. So let us see the plots. These are the three plots. One is showing what is how the transmittance through the mirror M2. So this is for mirror M2. So how this transmittance is changing, that is how the reflectance is changing. Then what we have, what is the cavity loss in this system where we vary the reflectivity of the mirror. And the third one is the laser output. So if you see the first interval, the interval here, if you see the transmittance is 0. That means the reflectance is nearly 100%. So whatever light is incidenting on the second mirror, it is getting reflected back towards the inside the cavity. So for this case, what is the cavity loss? The cavity loss would be low, right? And as the reflectance is high, we'll see that the laser output is negligible. Now next what we are suddenly increasing the transmittance of this mirror M2 to 100%. Let us say 100%. So that means now the reflectance is 0 and the cavity loss will be high. The cavity loss in the system is high, and as the transmittance is high, you will see a output in the system through the mirror M2. Okay. And now again we are switching off, we are changing the reflectivity to the 0. So that means again the cavity loss will be low and the output through this cavity will be low. So in this way, by changing the transmittance in periodic interval, what you can do, you can control the laser output through the mirror M2 and you will see a laser, pulse laser through mirror M2. So cavity damping, it is all related to how you are changing the reflectivity of the second mirror and um, generating a pulse laser through this second mirror. So energy, so its the definition says it is energy stored in the cavity is dumped by changing the output mirror transmittance or output mirror reflectance. And during off time, that is when there is no output through the laser, so you can see the resonator Q will be very high. Quality factor will be very high. So now we'll see what is Q switching. Okay. So we have covered external modulation, gain switching, and one of the method of loss switching, which is cavity damping. So now let us see what is Q switching. So these are some of the details that we have seen earlier. So let me uh, not go through this. Gain switching we have also discussed also by changing the by switching on and off the pump, we can change the laser output and we can get a pulse laser. So the next one is the Q switching. So these are some repetition. So let me not go through this. So this is the Q switching. So in Q switching, as I've said, we change the active energy stored in the active medium. So to change the energy stored in the active medium, what we use? We use a intracavity modulator. Okay. So by using so instead of a external modulation, we'll use a intracavity modulator and we'll change its transmittance in a periodic manner so that you can so that we can get a pulsed output through this cavity. And during this Q switching, the pump is already on. It is on over all interval of time, but the intracavity modulator, it will, because of the intracavity modulator, we'll see a pulse output through this cavity. So let us see how you can achieve this pulse modulation. So this intracavity modulator, it usually acts like a shutter. So shutter means it is open for a particular interval of time, and it is closed for a particular interval of time. So let us say it is open. So that means the transmittance T mode means. So let me explain this graph. So T mode means what is the transmittance through this modulator. Cavity loss is loss in the cavity, and what is the laser output. So if you see when T mod is off, so let us say initially the shutter is closed. So T mod is 0 means the shutter is closed, and T mod 1 or some non-zero value means the shutter is open. So when the shutter is closed, what will happen? So let me take a blank slide. So you have a cavity here, and you have the amplifying medium, and you have a intracavity modulator, which is this one. This is the intracavity modulator. So when the the shutter is closed, that is T mod is 0. So what will happen? Whatever light is incidenting on this modulator, it will not be able to pass through it. So what will happen? The light is concentrated in this region only. And because the light is not able to pass through this mirror, what will happen? So stimulated emission will not happen, because for stimulated emission, what you need? You need a external light. So we have this levels where N2, this is N1, the atomic population. And for to achieve the stimulated emission from here to from the E2 level to E1 level, you require a external light, external radiation. So because this external radiation is absent, what will happen? The atoms will continuously populated inside this level E2. They will not be able to jump into this state E1. And some may jump, some radiation may happen because of the spontaneous emission, because spontaneous emission do not require any external radiation. So the light that we'll see in the output will be spontaneous emission through this T mod equal to 0. So if you see so let me erase this one. So if you see when T mod is 0, the cavity loss in the system is high, and the laser output is 0. There will be no laser output when T mod is 0. Now when you open the shutter, when you modulate this external mod, the intercavity modulator, so when T mod is, let us say it is 1, that is 100% of light is passing through this T mod. So what will happen? Now the light that is blocked by this intracavity modulator, it will be able to pass through it. Okay. So now we take a different color. So now the light will pass through this intracavity modulator, and it will be able to oscillate back and forth between this laser cavity. And because of the initial condition, that is the initially we have T mod equal to 0, that is the shutter was closed. So the population in the N2 level is much greater than the population of N1 level. So because of that, we will see a high intensity of laser in the output, because the population is much greater than the initial case. And now what we'll do, we'll again close the shutter, And because of closing the shutter, what will happen? The light that was oscillating back and forth inside these two mirror, it will be blocked by this intracavity modulator, and it will be stayed inside this active medium. And because of this, what will happen? We'll see a gradually decreasing trend of this laser output. So in this way, by changing the transmittance through this external modulator, you can get a pulse laser output through the cavity. So basically, we are closing the shutter or opening the shutter. Okay. So I think this is clear to you. So let me move to our next part. So next part, it says comparison between cavity dumping and Q switching. So cavity dumping, we change the transmittance of this mirror M2, and but in Q switching, we change what is the energy stored in the amplifying medium, and we use a intracavity modulator to achieve a pulse laser. So if you see this figure, the transmittance through the mirror M2, it is periodically changing by changing the reflectivity. And according to that, you will see a change in variation in the cavity loss. And depending on the transmittance or reflectance, we will see a pulse laser output through this cavity. And in the second case, we change what is the energy stored in the cavity. And according to the opening and closing of this shutter, we'll see a pulse laser in the laser output. Okay. So this is all about what is cavity dumping and what is Q switching. Okay. So now let us see how you can achieve the Q switching. What are the methods to achieve the Q switching? So for cavity dumping, you can easily change the reflectivity of mirror M2. But let us see how you can change what is the transmittance of intracavity modulator. So for this case, what we can use, one is electro-optic modulator. Okay. So if you see this figure, so there is a material that behaves like a electro-optic modulator. So what happens during in this electro-optic modulator? So when we incident we are incidenting electric field into this electro-optic modulator, then we'll see a change in refractive index of the material. So according to the strength of the electric field, we'll see a change in refractive index of the material. And this change in refractive index, it will induce a change in phase of the output. So these are directly correlated. And this phase modulated beam, it can be transformed to a intensity modulated beam using a wave plate or polarizer. so So if you see this figure, so these are two mirrors. One is mirror M1 of reflectivity 100%. Another one is mirror of M2 with reflectivity 95%. And there is a active medium and there is a intracavity modulator. And what we'll do, we'll change will modulate this external modulator. So by changing, let us say we are incidenting a RF frequency. So when you apply a RF frequency, the refractive index of this external modulator, it will change. According to that, the phase will change, and according to this phase modulation, we'll see a intensity modulation of this electro-optic modulator. And the modulation we typically see the order in the range of gigahertz. Okay. And the next one is acousto-optic modulator. So in the first case, so we have by incidenting a external electric field, we are changing the refractive index and the phase and finally the intensity modulation. In acousto-optic, what we have? So we have a piezoelectric transducer, and we are incidenting a RF frequency here. And depending on the strength of this RF, what will happen? The light that is incidenting on this material, it will get diffracted. Okay. So because of the diffraction of this beam, we'll see that we'll see a intensity modulation like this. So, so this is the schematic of a grating amplitude modulator. So we have a grating where it consists of a light region or consists of a periodic variation of light region and opaque region and a covered region. So depending on the periodicity, what will happen? The light will get diffracted from here. And some light will directly pass through it, some light will diffracted in this direction, some light will diffracted in this direction. And this direction we say the first one is a first order diffraction, second order diffraction. So in this case, because of the change in diffractive index of the material, we see a change in phase, and depending on the change in phase, we see the acousto-optic modulator. It behaves like a intensity modulator. The output will be a intensity modulation. Okay. So now let us move to our next session. So this I think this is the schematic of what happens during the switching on the modulator or switching off the modulator or switching on the pump or switching off the pump. So this you already know. This is the variation of population inversion over time when you don't have any feedback. In absence of feedback, it will achieve a steady state population. But when you have a feedback, the population or the interpopulation will gradually increase. Then you will see a variation here. Then it gradually, this will gradually achieve a steady state population. Okay. So this we have already seen in our previous live section. Now you have an external modulator that will change this population inversion, population density. So when the transmittance, I think this is the resonator loss coefficient. When the resonator loss coefficient is high, so that means the gain will there will be no gain in the system. That is why you don't have any output in the third plot. So there is no laser output. So now when the alpha R, that is the resonator loss coefficient, or the losses inside the cavity decreases, that is it is low, then we'll see a pulsed output through this system. And in this way you see a pulsed output throughout this laser output system. And the pulse repetition rate, it is determined by the rate at which the losses are switched on and off inside the cavity or outside the cavity. And the pulse width, it is depends on the material properties. So in external modulation, you have external modulator, and by the rate at which you change the external modulation, then external modulation, you can achieve, you can control what is the pulse repetition rate of the laser output. Okay, so now let us see what is mode locking. This is the final method where you can achieve, we can generate a pulse laser output. So till now, do you have any doubt in any of the part? Okay, so let us see what is mode locking. So locking, by the definition, it says we lock the phase of all the longitudinal modes of the laser cavity. So we have a, let us say we have a laser where one is mirror M1 and then there is mirror M2. And because we have already seen earlier, depending on the round trip phase, we'll see that there will be longitudinal modes where nu q it is given by q times p by 2n. So these are the frequency at which we see the longitudinal modes. Okay. And now we'll lock the phase of all these longitudinal modes to achieve or to generate a pulse laser output through this mirror M2. So now let us consider a laser oscillating in a number of longitudinal modes, nu n, and this nu n, these are separated by free spectral range. So free spectral range, as you recall, this is nothing but the spacing between these longitudinal modes. So if it is nu q, it is nu q plus 1, nu q plus 2, nu q plus 3, and nu q plus 4. Right. And what is the separation between these adjacent longitudinal modes? This indicate what is the free spectral range of this cavity. And it is typically nu f is C by 2nl. Okay. So now we have a laser oscillating in a number of longitudinal modes nu n, and these are separated by free spectral range nu n. If you see this figure, this is nothing but the schematic of a output through a inhomogeneous broadening. So in inhomogeneous broadening, what will happen? If you recall, the loading at one of the frequency doesn't affect the loading at other frequency. So because the inhomogeneous broadening, it happens because of the interaction of the light, interaction of the pump with different groups of atom. So there is no relation between these longitudinal modes inside the cavity. Okay, so there is no relation. And so what we can assume the phase relation between these different types of longitudinal modes, must be random because there are different interaction, and due to the different interaction, the longitudinal modes, we are seeing the longitudinal modes. So initially we can assume the initial phase of these longitudinal modes are random. So there is no phase relation between these longitudinal modes. So now let us see how we can, what will happen when we log the phase of the system. So we take a particular phase and we uh, keep the phase of all this mode as phi only. So let us say we fix the phase of this longitudinal modes as phi. We'll see what will happen to the laser output. So for calculation purpose, let us take there are n longitudinal modes, that is uh, oscillating back and forth inside the cavity. So if you see this figure, so there are different longitudinal modes that are oscillating inside the cavity, and the electric field you can write it as this expression where n it is the amplitude of this nth mode, and 2 pi nu t it is the phase of it is nothing but uh, delta n. So not delta n because delta n is already taken as initial phase. So this is the phase of the nth longitudinal modes. And in this delta n, it is the initial phase that the mode have initially during the oscillation process. And ET, you can the resultant electric field. So we face so schematically. So there are cavity and there are n longitudinal modes that is oscillating inside these two mirrors. So the resultant electric field of this interacting mode, you can write it as this expression. Summation of n equal to 0 to n minus 1 an e to r I 2 pi nu t minus I delta. And nu n you already know it is nothing but q c by 2n. Or you can take it as n c by 2n. No, take q because q is integer. Okay. So nu n you can write it as nu 0 plus n times nu f. Okay. And nu 0 is the frequency of the first mode. So if you see the schematic, this is the intensity plot of the different longitudinal modes. So there is nu 0, nu 1, nu 2, and nu n minus 1. And these modes, these longitudinal modes oscillate only when it is the gain in this for this longitudinal modes is greater than this loss line. So this is the condition for amplification, right? The gain should be greater than loss. So let us say the gain for this mode is already greater than the loss in the system. So now let us see what is the total intensity of this multi-longitudinal mode in this cavity. So intensity is nothing but square of ET square. So if you take, so this is nothing but ET multiplied by E star T. So this is complex conjugation of this electric field. So this we already seen. This is the field we have, and this one is the complex conjugation of the first term. So this is the complex conjugation of the first term. So we have am star e to r minus I 2 pi nu 1 t plus I delta m. Okay. And for the case where this phase, so this, so let us say, so first case is where n equal to m. So when n equal to m, what will happen? This exponential term, they will cancel with each other and it will be 1. So that means we have only an square. Okay. So we have an square, summation of an square where n equal to m. But when is not equal to m, what we have? We have amplitude an, am star, and this is the phase term that we have for n not equal to m. And you can see the phase it is changing randomly with time. So depending on the phase, this factor will change. Depending on the initial phase, this factor will change. So we'll take a few approximation. So few assumptions. Let us say the amplitude of all this mode is equal, and it is equal to a. So that means the first term is n square. The second term we can, so this will become a square. So you can take it out from this summation. So the term we have is now this. So you can rearrange this to get this expression. So this after some rearrangement we get this final form. Okay. So if you see the maximum intensity will be Na square. So let me write down this expression. I is nothing but n mod a square plus some term here, right? There is a term here. So you can write it as n I0 plus some term here. And you can see this is the exponential term. So the maximum value that the exponential term can take is 1 and the minimum value is minus 1. So that means the maximum I max it is n I0 plus I0 and the minimum it would be n I0 minus I0. So this is shown in this figure. So this is, so let me erase this. So this is shown in this figure. This is how the intensity is varying when you have a random phase variation. So you can see the maximum is Ni0 plus I0 and minimum is Ni0 minus I0. And in between this, the output oscillate in a random manner. So this oscillation is periodic, although it is periodic, but because of the phase, the random relation between the phase, you see a phase out, sorry, intensity output like this. So this diagram is for the case where you have random phase relation between the longitudinal modes. Okay, and the separation between them is t equal to 1 by tau. Now we'll log the phase of the system. That is, we will fix the phase of the system. So as the name indicates, mode locking. Mode locking means all modes are in same phase. Okay. So if you see this expression, so this is, so now we have taken instead of delta n. So if you see, I think this one. For this ET, you can see there is a delta n term here because the n modes have different phase. That is why we have taken delta n, which is variable. Depends on the value of n. But in mode locking, we have taken delta n as, so if you see this, we have taken delta n as delta 0. That is, all modes have the same phase, which is delta 0. Now, if you solve this, so this is omega n. So omega n is nothing but 2 pi nu n, right? So, and nu n is nothing but, this is nu n, which is nu 0 plus n times nu f. So you just have to put this expression for omega n here. If you put it, the final form that you, so just take out the constant factor, nu 0 is constant. So if you take out the constant factor, which is e to power I delta 0 and e to power I 2 pi nu 0. So the expression that the summation is now, it is simplified and it is summation of n equal to 0 to n minus 1 e to power I n 5. And this, if you recall the binomial expansion, this expression you can solve it. So if you see this, so just follow this formula to get this expression of intensity. I think it is easy to solve, so I'm not going through this. Okay, so intensity. So when phase is locked, now we have intensity which is varying like this. So intensity is given by mod a square sine square n phi by 2 divided by sine square phi by 2. So if you plot this intensity now, if you see this figure, this is the intensity variation of a phase lock system. So now let us see what is the peak intensity, what is the minimum intensity, and where we are getting the maximum intensity and where we are getting the minimum intensity. So when the phase is locked. So now the intensity, as we have seen, it is given by this expression, and phi it is given by 2 pi nu f t. For minima, what you need? So if you want to get a intensity 0, that means this term it should be 0, right? So that means n phi by 2 should be p pi, where p is some integer. So that means intensity is 0 when the phi, that is the phase, it is given by p into 2 pi by n. So please remember n is the number of longitudinal modes that is oscillating inside the cavity. So I equal to 0 when phi is p times 2 pi by n, and p is 1, 2, 3. And for maxima, what you want to have? For maxima, it should be pi by 2 equal to m pi. That is pi equal to 2m pi. So some even multiple of pi. Okay. So this is where you can get maximum intensity. And what is the maximum intensity that you can get? It is detailedly explained by professor in during the lecture. So if not, let me uh, so for minimum intensity, what we have? So let us take n phi by 2 is p pi, right? So so if you see this, then for this we'll see a 0 by 0 form. And if you take the derivative and if you follow the L'Hopital's rule, you can get the intensity as n square. Okay, this term you get as n square. So that means the maximum intensity that you can get during the phase locking system is n square times I0 when pi is some even multiple of pi. So if you recall, when the phase is not locked, I max, it is n times I0 plus I0. But when phase is locked, you can see how higher the intensity can get. It is n square times I0. So by taking a phase locking system, you can see the intensity varies like in a pulsed manner. Okay, so we'll understand this by taking one example. So let us say take. So this is, I think, n equal to 5 they have solved. So for n equal to 5, what is the minima? What is the point where we will get the minima? So for minima, n phi by 2 should be equal to p pi, right? And n is already 5. That means pi is 2p pi by 5. So that means these are the point where you will get the minima. So p may be p is 1, 2, 3. Means this point here, it is 2 pi by 5. Next point here will be 4 pi by pi. Similarly, when the p is 5, so let's say p is now 5. So for this case, pi will be 2 pi. So instead of minima, you will get a maxima here. Similarly, then we'll see minima, then maxima. You can see the intensity is similar to a pulsed manner, behave like a pulsed output. And the maximum intensity will be 25 times I naught n square times I0. That means 25 times I naught. And the separation between this peak. So if you want to find out what is the separation between the peak, what you have to do, so you can see the phase difference, it is 2 pi. That means phase difference is 2 pi, and phase difference is nothing but 2 pi nu f delta t, which is equal to 2 pi. So that means the separation between this peak in time is given by 1 by nu f. Okay, so which we write it as Tf. So in this way, you can calculate what is the separation between the peaks in time, which is given by Tf, and Tf is nothing but 1 by nu f. And if you want to find out what is the width of this peak, so for width, what we can do, we can equate this phase, this delta phi, to 2 pi nu f delta t. Now the delta phi will be 2 pi divided by n. Okay. And from this, you can find out what is the width of the peak. Width of the peak, it is given by Tf by n. Okay. So this means, to summarize, 1 minute. To summarize, when we have a phase log system, that is the initial phase of these different modes, it is same and it is nu zero, then the intensity varies in this manner, and the peak width of this pulsed width of this intensity peak, it is given by Tf divided by n. N is the number of longitudinal modes in the system, and these peaks, this intensity, these are separated by Tf, which is equal to 1 by nu f. And nu f, if you recall, it is given by 2L by C, right? So that means if you see this term, so it is nothing but the time taken for one round trip. So let us move to the next one. So if you see this figure, so it consists of two mirrors, mirror M1, mirror M2, and the separation between them is L. And the one round trip time will be the path, total path covered, which is 12, divided by the speed, which is C. So that means this when phase is locked, we'll see a pulsed output over each round trip. Okay, we'll see a pulsed output over each round trip where the separation is Tf, which is the time taken for one interval, and the width is Tf by divided by n. So let us summarize this. So when you have a phase lock system, that is the train of periodic high intensity pulses. So you will get when you have a phase lock system, you will see a train of periodic high intensity pulses which are separated by a period nu f, and the peak intensity, it is given by n square times I0, and this is equivalent to one high intensity pulse making round trip in the cavity. Okay, because these pulses are separated by Tf, which is nothing but the time required for one round trip, we say this is equivalent to one intensity pulses making one round trip in the cavity. And width of this pulse, it is as we have seen, it is given by Tf divided by n. So that means the width is now it is determined by the number of modes that is oscillating inside the cavity. So these are some information, that is, after covering length 12, each time pulse is given out and leading to a pulse output with pulse separated by Tf, which is 12 by C, and in space it is separated by 12. Okay, so this is all about the mode log system. Now we'll see how you can achieve a mode locking. So how you can achieve a constant phase during the oscillation process. So do you have any doubt till now? Okay. So if not, let us move to our next part. This is the final part of week 10. So after this, we'll solve few problems like some additional problem related to week 9. So let us see. So these are the summary of what we have seen earlier. That is, in a mode log system, in a phase log system, where the phase of all longitudinal modes is constant. It is given by delta zero. Then it is possible to achieve a pulsed output where maximum intensity is given by n square times I zero, and the peaks, these are separated by TF, which is equal to 2L by C, and the width is given by TF by N. And this is equivalent to the one round trip uh, path of a high intensity pulse. Okay, so to achieve this, that is to, so if you recall, during one round trip, high intensity pulse is oscillating inside the medium. So to filter out this high intensity pulse during this round trip, what you want? You want a shutter which is time, which opens during a time interval which is much less than 12 by C. So if you take an example that is L equal to 10 centimeter, then you can see how small this time is. So how small the opening time of the shutter will be to achieve this, to filter out this high intensity pulse during the round trip. So for that, what we can do, we can approach two methods. One is active mode locking. 1 minute. Okay. So one is active mode locking and one is passive mode locking. So these are two methods. So in active mode locking, we modulate the amplitude of the mode. So that is by modulating the loss in the cavity, we modulate the amplitude of the mode. And depending on the amplitude modulation, we'll see that the phase of these oscillating modes are they are in phase. That is, the phase is constant. So now let us see what is amplitude mode locking. So in initially we have, let us say we have one mode which is at frequency nu f, and we do this amplitude modulation around the frequency nu f. Okay. So ET for this mode, it is given by, let us say it is given by A0 cos nu 2 pi nu 1 t. And by, so in the next step, we change the amplitude of this ET by adding one sinusoidal term, which is B cos 2 pi nu ft. So this is the amplitude modulation at frequency nu f. Okay, this second term. So in the next part, what it has been done. So just have to multiply and take the sum of this individual term. So we have to multiply this and this with this. So you can get a term A0 cos 2 pi nu 1 t and a term which is looks like this. So this you can get it from here. So if you see the second term, that is the multiplication of this with the second term, we can get B cos 2 pi nu ft multiplied by cos 2 pi mu 1 t. So this is nothing but cos A cos B. So you can multiply 2 here divided by 2, and 2 cos A cos B. If you recall, it is nothing but cos A plus B plus cos A minus B. And so this is what has been done in this case. So A is nothing but mu 1 t, B is mu f t. Now if we solve it, so if you see this, there is one term which we have already had before the amplitude modulation. So if you see this term, this is the one we have earlier. Now, when you modulate the amplitude at a frequency nu f, what you have? You have three terms. One is the initial one, and one with frequency nu1 plus nu f, and another one with frequency nu1 minus nu f. So that means in addition to this initial longitudinal modes, we have side bands. One is this nu1 plus nu f, and another one is this nu1 minus nu f. And these modes have they oscillate in phase. That is the nu n for all these nu f, sorry, nu1, nu0, nu1 plus nu f, and nu1 minus nu f. The phase is constant, and we can take it as some value which is nu0. So in this way, by changing the amplitude of the system around frequency nu f, you can see we can log the phase of the oscillating longitudinal modes, and we can get a pulsed output. In the passive mode locking, it involves a saturable observer. So if you recall, saturable observer are nothing but the material which have higher value of loss coefficient but lower value of saturation intensity. If you see this figure, the gamma, the loss coefficient is high, but IS is very small. And using this saturable observer, you can get a pulse output. So now let us see how you can achieve a pulse output using passive mode locking. So, so let us go through few details of this passive observer, sorry, saturable observer. So if you see, when the intensity, let me take a, so if I zoom this, so that means this is like this. And when the intensity it is crossing the IS value, you can see how the loss coefficient is decreasing rapidly. So that means when the intensity is it is less than IS, the loss of the saturable absorber is high. That means it behaves like as a shutter which is closed. But when the intensity is greater than IS, so the loss coefficient of this saturable absorber is low. That means it behaves like a shutter which is open. Okay, so it will pass the light when the intensity is greater than IS, but it will block all the lights when the intensity is closed. Sorry, when the intensity is less than IS. So in this case, in passive mode locking, we are not. So let us. So we are considering the case where the phase is not locked. So if you recall, when the phase is not locked, I think this slide, when the phase is not locked, you can see the intensity is like this, or you can see this figure. The intensity varies in this manner. And the maximum is Ni0 plus I0 and minimum is Ni0 minus I0. Now let us see what will happen when we have a passive observer in this not phase locked system. So if you see, if the let us take, if the IS level is here, what will happen when we pump the system? This intensity, it will gradually increase, it will level off in the y-axis. And at some point, what will happen? If you see, so let me take a different color. So if you see this plot, for this reason, the intensity is greater than IS. So that means the passive absorber, the losses in the passive absorber will be low, and this intensity will pass through this passive absorber and will seen as a laser output. But if you see the uh, intensity that is here, that is around here, for this case, the losses, the IS level is higher than the intensity. So that means the losses in the saturable absorber will be high, and it will block this intensity. It will not. It will absorb this intensity and will not pass this intensity to in the right. So that means you won't see any laser output of this intensity pattern. So in this way, what will happen? So as the intensity is varying in a periodic manner, so only where this intensity where I nu is greater than IS, so I is greater than IS, this will pass through this uh, saturable absorber, and we'll see a laser output in the right side. But when the intensity is lower, that is this region, and this region, this will not be passed through the saturable absorber because these are absorbed by this saturable absorber. So in this way, you will see pulsed output through this laser system. Okay, so if I plot clearly, you will see a pulsed output when you have a saturable absorber. And what are the example of saturable absorber? One is methylene blue, and another one is cryptosan. Okay, so as I've said, only the peak where the intensity is higher than IS, it will be passed through the saturable absorber, but the peaks where the intensity level is lower than the saturation intensity, it will not pass through the saturable absorber. And for this to happen, what we need that the relaxation time of the saturable absorber should be extremely small, so that when the intensity, so if you see, you made this. So if you see when the intensity is going from high to low, for this low case, the loss in the observer should be high so that it will be filtered out. So that means the relaxation time of this saturable observer should be extremely small so that it can come back to the high loss state after passing one peak. Okay. Otherwise, you won't see any pulse output. So this summarizes the mode locking system. So now we'll see some of the examples. One is output from a Q switched fiber laser. So this is the output. You can see you can get a pulse output by means of Q switching, and the line width of this pulse is around 88.3 kilohertz. And if you take a zoom in picture, you can see this is the plot where the width is around 238.2 nanosecond, and there are different parameter, that is rise time, fall time. You can see although this pulse is not symmetric, but by means of Q switching, you can get a pulse output. Okay. So this is also one of the recorded train of mode locked pulses. You can see how narrow these pulses are. That is, you see the width is around 1.439 nanosecond. Okay. In addition to these pulses, the pulse laser, we have ultra short pulses where the pulse width it is of the order of 1000 femtosecond or 10 femtosecond or in between this range. So it is in the order of femtosecond. So you must have heard of femtosecond laser. So for that laser, we have line width which is around femtosecond, and these have wide application. That's for ultra fast phenomena. Okay, but when you take a quick switch laser or a Morlock's laser, the tau, that is the line width, the pulse width is of the order of nanosecond or picosecond. So it is not on the order of femtosecond. Okay. So to get this ultrasonic pulse, what we do, we use non-linear optical effects in a dispersive medium. So let me skip this part. So this has already been discussed in the lecture. So please go through the lecture video. And this is intensity autocorrection. It is the method at which you can detect the ultrasound pulse. Because normally the detector will not be able to detect this ultrasound pulse. So to detect the ultrasound pulse, what you do? We do a intensity correlation. So if you see the schematic, there is a pulse, which is ultrasound pulse. It is passed through a beam splitter. So what will do? What this beam splitter will do? So this will split the beam in one direction, in another direction. So these two beams, they cover different paths and they interact with this non-linear crystal. And what will happen? The non-linear crystal will see single harmonic generation in the non-linear crystal, and this single harmonic generation will be detected by the detector. Okay, and so let me give a brief overview. So what we do during intensity autocorrelation, so we change the time delay, the pulse delay between these two parts. Depending on the pulse delay, what you can see. So one pulse is coming like this, and there is another pulse where we are changing the time delay. That is, the pulse is here, or the pulse is here. So it moves in this range. And when this pulse overlap this the initial pulse, then we'll see a spike in the intensity. Okay, so this is where the two pulse overlap with each other, and this is the background which is given by this single harmonic generation. Okay, so by changing the path length, let us say by changing when you for 1 centimeter the path length, so the pulse width it is around 10 to the minus 10 seconds. But when you control the path length of the order of 1 micrometer, you can see you can achieve the femtosecond pulse detection. Okay, so this is all about week 10 content. So we have covered what are the different types of pulse laser, how you can achieve different types of pulse laser, and we have also covered what are the ultrasound pulses. Now let us solve few problems that is related to the week 9 concept. Okay. So we'll solve few problems now. And this is not required. Okay, the first question is okay, so let us solve from here. So the question says a Fabry-Pérot resonator is formed in a medium of refractive index 1.5, and if the separation between the reflecting end is 40 centimeter, what is the free spectral range of this resonator? So you have a Fabry-Pérot resonator where is given the refractive index is 1.5. The separation between this the reflective end, which is L, this is 40 centimeter. Then the free spectral length. So what is free spectral length? So this is the separation between the adjacent modes. Separation between them. And if you recall for uh, Fabry-Pérot, the nu P is given by PC divided by 2nt cos theta. And N is the refractive index, T is the spacing between the atelia, P is an integer, and cos theta is the tilt angle. So if we take tilt angle is 0, so that means nu P is equal to P by 2nt. So that means the nu F should be P plus 1 minus nu P, which is given by C by 2nt. And C, you already know it is 3 into 10 to the 8 meter per second, 2 into 1.5 into T is nothing but L, which is 40 centimeter, 10 to the minus 2. So the answer we will get is around 250 megahertz. So the free spectral range for this Fabry-Pérot resonator, it is around 250 megahertz. So option D. So now let us move to the next problem. So the next problem says a laser emits a frequency of 800 terahertz with a line width of 2 nanometer. Calculate the corresponding coherence time and coherence length. So let us see what is given. So frequency is given, it is 200 terahertz. So please recall 1 terahertz is 10 to the 12 hertz. So the next thing which is given is delta lambda, which is 2 nanometer. So coherence length, so coherence time. So let us see what is coherence time first. So coherence time, it is nothing but 1 by delta nu. And delta nu you can calculate from this expression relation, which is nu equal to c by lambda. If you take delta nu, it will be c by lambda square. So mod of delta nu, it is c by lambda square into delta nu. So if you are given delta lambda and so you are not given lambda, right? So lambda you have to calculate it from nu. So instead of doing that, let us multiply C here and divide a C here. So that means this is C by lambda square. So this is nu square by C delta lambda. And nu C and delta lambda, these are already given. So that means delta nu is 200 10 to the 12 square 2 nanometer 3 into 10 to the 8 meter per second. And if you calculate it, you can get around, I think, will come around 4.266 terahertz. And once you calculated delta nu, then calculate what is the coherence time, which is 1 by delta nu, and it is 1 by 4.266 into 1 minus 12. So this will come around 0.234 picosecond. So 1 picosecond is 10 to the minus 12 seconds. So this is the coherence time. For coherence length, what we have is C times tau C. C we already know it is 3 into 10 to the power 8 meter per second. Tau C is 0.234 into 10 to the power minus 12. That means it will come around 70 micrometer. So this is tau C we got and this is LC we got. So let us see what is the answer. So this is the answer, which is tau C is 0.23 picosecond and LC is 69 micrometer. Now let us see our next problem. So the next problem is about the angular divergence of the laser beam. So you are given a output from a fiber laser which is projected on a screen kept at a distance of 10 centimeter. And if the diameter of the laser beam observed on the screen is 1.4 centimeter, then what is the angular divergence of this laser beam in radian? If you recall, when the laser beam propagate, so there is a small divergence angle associated with the laser beam. And to calculate it, so if you are given a laser spot, this is the diameter. And if you are given the length at which you are seeing this laser beam diameter, then what is this will be the divergence angle. So tan theta you can take it as d by 2 divided by L. So theta will come around tan inverse d by 2L. And d is already given. So this is the diameter. So diameter is 1.4 centimeter. And the distance L it is given, it is around 10 centimeter. This one. So that means if you put all these values, then you will get theta is 1.4 divided by 20. So it will come around 0.1398 radian. So this is the divergence angle after covering a distance 10 centimeter. So now let us move to our next problem. So the next problem says a Michelson interferometer experiment is to be performed using a sodium lamp, which is wavelength around 590 nanometer with line width of 0.6 nanometer. Then the two mirrors of the interferometer are kept on movable mounts. Then the permeable path difference between this interfering beam coming from these two mirrors should be. Okay, so what is the path difference? What is the path difference between these two mirrors such that we can see a clear fringe pattern in the screen? So to calculate the power difference, what we know? So the maximum power difference should be less than or equal to LC, right? Maximum permissible power difference between the two beams should be less than or equal to LC. Otherwise, what will happen? The beams will become incoherent. So there is no phase relation between them. So because of that, we won't see any fringe pattern. And LC, so let us see what is given to us. Lambda is given, it is 590 nanometer. And line with delta lambda is given, which is 0.6 nanometer. And for LC, it should be C times tau C or Tc, which is C times delta nu. And you can write it as C lambda square divided by C delta lambda. That is lambda square by delta lambda. And all these are given. So LC would be lambda square by delta lambda. That is 590 to 10 to the minus 9 square divided by 6 nanometer. And this will come around 0.58 millimeter. So you are given two options. One is greater than 0.58, one is less than 0.5. So for our answer, that is to see a clear image, clear fringes, we need the power difference should be greater than the coherence length. So that means LC should be less than equal to, sorry, the power difference should be less than equal to, power difference should be less than equal to LC, which is 0.5. So the answer will be option 8. Okay. So now let us move to the next problem. So next problem is a conceptual one. So it says, it is observed that when an intracavity etalon is placed inside the cavity of a particular multimode resonator, multimode laser, then the output power drops drastically to zero, almost zero. Then which one of the following not a correct explanation for this observation? So that is, you have a resonator system and you have a etalon, intracavity etalon. So if you recall, intracavity etalon are used for single mode laser, right? If you have a multi-mode laser oscillation, then by using intracavity etalon, then you can get a single mode laser. Now the question says, when you put the intracavity etalon inside this cavity, then the transmittance, that is the output power, drops drastically to zero. Then what is the possible reason for observing this effect? One is option 1 says the tilt angle of etalon is not adjusted properly. So this is right because depending on the tilt angle, the resonance frequency of the etalon as well as the cavity, they will match or they won't match with each other. So depending on that, we will see a drastic change in the power. So this is right. The second is resulting loss in the cavities above the gain of the active medium for all resonance frequency. This is also right because when the gain is lower than the loss in the system, this is loss, this is gain. When it happens for all frequency, that means there is no amplification inside the medium. So that is why this option is also correct. The next option is there is no overlap between any resonance frequency of the cavity with that of etalon. So this is also right because when they don't overlap with each other, then how you can see the output power. Only when they overlap with each other, then the fabricated cavity will transmit that beam and we'll see a laser output. So that means this option C also correct. So the remaining will be the option D, which is incorrect. So let us see option D. So option D says the free spectral range of the laser cavity is more than the free spectral range of ethanol, which is not correct because free space FSR of cavity is much smaller than the FSR of ethanol. We have seen in the lecture also. So that means this is the reason behind the case where when you put the ethanol inside the cavity, we are seeing it dropping in the output power. So answer will be option D. So let us see the next problem. Okay. So the next problem is a laser with an intracavity ethanol operates at lambda equal to 1064 nanometer and has a mirror separation L equal to 10 millimeter. Then the question is asking what is the free spectral range of this ethanol and what is the total number of modes that can fit within the bandwidth of 5 nanometer around the laser wavelength. So let us see the question one first. So FSR, you already know it is given by C by 2NL. So if you, I think this we have already solved. Question two, it is given by C by 2NT. So that means for this case also it is C by 2NL and what is given, L is already given. So that means it is 3 into 10 to the power 8 divided by 2 times N it is not given. So we can take it as a 1 and L is 10 millimeter. It is 10 into 10 to the minus 3. So that means FSR you can get is 1.5 into 10 to the power 10 hertz. So this is the FSR. Now the uh, next part asks what is the total number of modes that can fit within the bandwidth of 5 nanometer around the laser wavelength. So you have a laser wavelength and its bandwidth is 5 nanometer. Then in that wavelength, in that bandwidth, what is the total number of modes of this ethanol that can fit inside this 5 nanometer? So for this case, what you have to do? So you have to express the FSR now in terms of nanometer. So in the first part, we got FSR in terms of hertz, that is time. For to calculate the total number of modes, because you can see bandwidth is given in terms of nanometer, right? 5 nanometer. So if you express the FSR in terms of nanometer and then by dividing the bandwidth with FSR in nanometer, you can get what is the total number of modes that fit inside this laser. So FSR is nanometer. So how you can convert from nanometer to wavelength? From hertz to nanometer. So for this, you can use this relation, which is C by lambda. So delta nu equal to C by lambda square delta lambda. So that means delta lambda is lambda square by C delta nu. So we want FSR in nanometer, right? So that means lambda is given 1064 nanometer, 4 into 10 to the minus 9 square. Delta nu, we have already calculated 1.5 into 10 to the 10 divided by 3 into 10 to the 8. So if you calculate it, all these parameters, then you can get around delta lambda is 0.0564 nanometer. So this is the FSR in nanometer. So that means the number of modes that fit inside a 5 nanometer bandwidth will be FSR in nanometer divided by bandwidth, which will give 5 nanometer. Sorry, this would be other way around, right? Bandwidth divided by FSR. Divided by FSR in nanometer. So bandwidth, it is given 5 nanometer. FSR, we have calculated it is 0.0564. So it will come around 88.5, which you can round it up to 88. So that means in this 5 nanometer bandwidth, total 88 number of modes can fit. Okay. So let us quickly solve these two other problems. So the next problem says, what is the laser cavity has a length of 1.2 meter and operates at a wavelength of 800 nanometer. If the cavity length changes by 0.5 micron due to mechanical vibration, then calculate the change in the laser frequency. So if you recall, as we change the laser frequency, sorry, as you change the refractive index or laser cavity dimension, then the frequency get changed. So if you recall, the delta nu by nu is delta n by n plus delta L by L. And delta n by n, we are ignoring this part. So that means delta nu by nu is delta L by L. And delta nu should be delta L by L. So delta L is already given, it is 0.5 micron. And L is given 1.2 meter. And nu is given by C by lambda, that is 3 into 10 to the power 8 divided by lambda is 800 nanometer. So if you solve this, you can get around answer around 156 megahertz. Okay, so this is the answer. So now let us quickly solve the last problem. So the last problem says a laser cavity with a length of 2 meter and refractive index of 1.6 is used. The temperature changes by 2 Kelvin, causing a refractive index change of 2 into 10 to the minus 6 Kelvin inverse. Calculate the resulting change in the laser frequency and the fractional stability. So to calculate the resulting change in laser frequency, you can use this formula, which is delta nu by nu equal to delta n by n plus delta L by L. So now we are ignoring this part because it's not given. So we are assuming the cavity length here remains constant. So that means delta nu by nu is delta n by n. And delta n, it is given 2 into 10 to the minus 6 per Kelvin. And for 2 Kelvin change, so you can see the temperature changes by 2 Kelvin. So that means delta n is 2 into 10 to the minus 6 into 2. So 4 into 10 to the minus 6. So delta nu will be 4 into 10 to the minus 6 divided by 1.6. Nu is okay. So resulting change in the laser frequency. So nu you can calculate using the given parameter. So nu is directly not given. So nu you can calculate by C by 2NL. So C is given 3 into 10 to the power 8 divided by 2. Refractive index is 1.6. L is given 2 meter. So it will come around 4.6875 to 10 to the power 7 Hz. Okay. And from from nu delta nu, you can calculate it by using this. So it will be 4 into 10 to the minus 6 divided by 1.6 into 4.6875 to 10 to the power 7, which will come around 117.1875 Hz. Okay. And for the frequency stability, so frequency stability is the fractional language. Frequency stability is given by delta nu by nu, which is nothing but delta n by n, right? Which is 4 into 10 to the minus 6 divided by 1.6, which will come around 2.5 into 10 to the minus 6. This is the answer. So in this way, you can solve this problem. Okay. So for today, let us end this session. So what we saw, we covered what is the week 10 content, that is about the pulse laser, how we can achieve the pulse laser, and what is the different methods of achieving the pulse laser using either external modulation or cavity damping, loss mechanism, Q switching. So and we have also solved few problems that is related to the week 9 concept. So in the next live section, we'll uh, discuss the concept that is related to week 11, and we'll also solve few additional problem that is related to week 10 content. Okay, so thank you for joining the section. I hope whatever I have discussed, it is clear to you. If not, feel free to ask me during the live section or feel free to write in the discussion forum. Uh, we'll try to answer all of your queries. And let us meet for now. Let us meet on next live session, which is on Saturday from same time 4 to 6. Okay. So thank you for joining the section. Let us meet on the next Saturday. So goodbye, everyone.